Hello, my name is Benjamin Francolini, and I am a master's graduate student in the Alternative Fuels Laboratory at McGill University. Identifying sustainable technology that can meet global energy demand and comply with emissions legislation remains one of the biggest challenges we face today to mitigate climate change. In 2019, the International Energy Agency demonstrated that the use of fossil fuels accounts for approximately 80% of our total primary energy supply. Considering our energy demand will only continue to rise in the coming years, it is imperative to curb our dependence on fossil fuels as a means for reducing our carbon footprint. Therefore, a rapid transition to sustainable fuels, such as green hydrogen, is necessary to solve the climate problem, and is technologically feasible in existing gas-fired power plants. Hydrogen is a promising sustainable fuel that can be used in power plants because its combustion produces water vapor instead of greenhouse gases like carbon dioxide. Nevertheless, there are challenges to substituting hydrogen for natural gas, which is conventionally used in gas turbine power plants and whose primary constituent is methane. Considering hydrogen is both light and highly reactive, a gas turbine combustor operating on hydrogen is prone to a phenomenon called differential diffusion. Consequently, flame instabilities arising from differential diffusion can result in blow-off, where the flame propagates downstream, and flashback, where the flame propagates upstream. The onset of these instabilities can significantly damage turbine components, delay energy production, and lead to safety hazards. Therefore, if hydrogen is to be safely incorporated in gas turbines along with natural gas, then a fundamental understanding on the behavior of methane flames in response to adding hydrogen is required. My thesis aims to characterize these flames, which are prone to differential diffusion, in a swirl combustion configuration, which is widely adopted in gas turbines. Swirl combustion is popular in gas turbines because it is an effective method at stabilizing flames for continuous and robust operation. However, my thesis investigates low swirl flames over high swirl flames because they can decouple flame instabilities through the mixture composition, which helps to determine which percentage of methane to hydrogen is problematic. Through laser diagnostics such as particle image velocimetry and combined planar laser-induced fluorescence, my work will relate velocity and heat release of methane flames with increasing hydrogen content in order to underline their stability. Going forward, the data obtained from this study will encourage design improvements to ensure gas turbines are better poised to handle hydrogen-enriched mixtures in the future. Most of all, it will enable the combustion community to further understand how best to utilize mixtures with high hydrogen content in an effort to reduce greenhouse gas emissions. Thank you to McGill, Siemens Energy, and the RQAI Fund for their continued support of this project.